Today's class we're going to see the different concept is called the open circuit, short circuit, and different voltage sources concept. We'll go through this session. So let us consider the open circuit. Open circuit. So the definition of this open circuit here is when there is a break in any part of the circuit that part said to be open circuited, said to be open circuit. So that is the statement is given to for open circuit concept. So here, to understand these concepts, let us consider a simple DC circuit of consists of different resistors here. In this, the voltage shows different resistance R1, R2 and R3 is there. So whenever if you see a closed circuit and if it is connected or excited with this particular sources, so it is going to supply current through this. So this is a closed circuit, this is the current flowing in a circulating in this closed circuit I. If suppose due to any incident or any kind of condition, if the resistance which is connected across this AB terminal R2, if it is opened, if it is removed, then the equivalent circuit can be drawn here as be like this, the voltage and R1, R3. In between this AB terminal, I'm simply removing this R2 element. So this is called the open circuit condition. Now my circuit is in open circuit condition. And during this open circuit condition, what is the current and what is the voltage need to analyze. So when there is open circuit means no closed path, consequently no current flows through the circuit, flows through the circuit. So here I can say the current I can be 0 amperes. Here no current is flowing, here also current I can write 0 amperes, because during the open circuit my resistance in the open circuit is almost infinite resistance, R infinite you can say. So for the R infinite circuit, for open circuit condition, no current is flowing through this circuit, there is no closed path, so there is no current is flowing. So whatever the current is flowing in the R1, in this condition is 0 amperes. Similarly, you can see in the R3 also the 0 amperes. As this is the 0 amperes, the voltage drop also you can say 0 volts. Here also you can say the 0 volts is the voltage drop. If this is the 0 amperes 0 voltage drop, so can I say it is become a short circuit? There is no current, no voltage drop. This is look like a short wire. It is look like a short wire. Then here whatever the voltage source, the potential is available here, that is going to appear across this terminal. So this is what the condition. In case of open circuit, open circuit, open circuit of any network, the whenever it suddenly opens, that condition that R across the AB terminal is infinite resistance, so there is no current is flowing there, and no current is flowing, so the voltage across the AB terminal is also equal to the voltage across AB terminal is also equal to the source voltage. So that is the point you need to understand here. Now comes to the second concept. You can call it is short circuit, short circuit, short circuit. So the short circuit is a low resistance path. Short circuit is a low resistance path. Low resistance path. When the short circuit occurs, the current flows through that short circuit path only, that short circuit path only. So that is the statement I'm giving here. So we'll understand this one. So I'm taking you can take here a network is like this, have different R is there, and my two elements has been connected something like this, and voltage plus minus, and R1 R2 is there. So this is that the normal condition. My circuit has been there, and whenever this circuit is there, then there is a current is circulating through it. There is a current circulating through it. I is fine. It's going the same current I here and coming back here I. So this is this is the normal condition of my circuit. Now I want to create a short circuit here. Short circuit is nothing but simply a short the circuit in between the any terminal A, B. In the AB terminal, I'm short this particular network. So short circuit means we are going to take the wire. That wire has a zero resistance. This wire has zero resistance, and it is going to short in between if these two terminals. Then what could be the scenario? That is what I want to take here. Because now I done the short circuit condition, now I need to see what is my current direction here. So you need to remember one point here. Note, always the current try to flow through the low resistance path. Try to flow through the low resistance path. So this is the statement I'm giving here. So according to this, when the short circuit has been created in between these two terminals, so whatever the current I is going before through this R2 resistor, it doesn't go here. This total amount of current flows through this short circuit, this line. So in this condition, when the short circuit has done, my current is flowing R1 and this short circuit line and this like this. This is my current direction now. So whatever the current flowing in the R2 at this particular moment is, you can say, 0 amperes. When the short circuit has done, there is no current is flowing through R2. Whatever the current is flowing through the short circuit path, minimum resistance path. So minimum resistant path, this current is flowing in this direction. Now we'll take the another scenario here. Same network, some I'm considering in different way here. So same network I'm considering here, but my short circuit I'm going to create in different way here. So before that, this is my current. So before that, my current is, this is my current direction. I is going like this, like this, like this, and like this, and coming back. But here, if I create a short circuit like this, short circuit or low resistance path like this in between at this moment here, so there is no current is flowing here, 0 amperes, 0 amperes, whatever the current I is flows like this, you can say. So this is what the closed path here. So this is what my closed path and through which my current is flowing. So this scenario you can call that dead short. This scenario you can call the dead short, because there is no purpose for creating the short circuit. Create this like this, then there is no current is flowing with these particular loads. So what is the use of this? So that's why it is called the dead short circuit. It is. Now I will take the another configuration here. Now my want to see different configurations here. For that I need one more network I'm going to consider here. So this is one more network. VI is current, R1, R2 and R3 is there. So this is the network. Here my current is dividing in different ways, I1, I2 and I3. So this is what I want to take this network, and for this network, if I create, if I in middle of this network, in the third R3, in the middle of this R3 resistor, from this point, if I make a short circuit like this, from this point, if I make this kind of short circuit like this, then this short circuit is called partially short circuited. Partially short circuited. Partially short circuited. But what is the direction of my current now? So here there is no change. Here same current I1 is flowing, no problem, and I2 is flowing, no problem. Here my current direction now is going to be, my current I3 direction is, previously it is flowing through the resistance, through the whole resistance value. Now my resistance, my current direction is coming like this, coming like this, coming like this, going like this. So this is my current direction now. This is my current direction now. So this is the amount of resistance has been neglected whenever we are creating a short circuit from middle of this particular R3. So during this partial short circuited, my R3, my R3 value has decreased, isn't it? My R3 value has been, the effective value of my R3 has going to be coming down, so decreased. So this is what my current direction is coming through the short circuit. Instead of by excluding this part, whatever the short circuit we have done through, my current is flows like this. So this kind of open circuit and short circuit concept we need to understand, because when we are going to further study of our BTech in electrical engineering in the second year and onwards, we are going to deal with the power systems. So in the power system, you need to have the power system transmission lines, generating stations we have. So there a sudden faults has been occurs. So sudden faults, if you have the three lines, the transmission lines are going like this, suddenly the short circuit has been going to be occurs. So then what is the condition of my fault current and what could be the consequences, and those concepts we need to understand. So for that you need to go for a concept is called the short circuit and open circuit and short circuit concepts. Now we'll go for the different types of energy sources. We have different type of energy sources. Further, these energy sources are classified as independent energy sources and dependent energy sources. Dependent energy sources. So here these independent sources are, again, this is voltage source and the current source. Again, this voltage source are can be classified here ideal voltage sources and the practical voltage sources. Similarly, this is also can be classified here ideal as well as the practical voltage source. So these are the different classification. When it comes to the dependent voltage sources, here we have current, you can say voltage control voltage source and voltage control current source and current control current source and current control voltage source. So these are the four classification we have. If you want to see the symbolic diagrams for this concept here, this is what the voltage source, which is controlled by the voltage variable. For this is the control on this is the current source. This is current source controlled by voltage, and this is also a current source controlled by uh, current, and this is my voltage source controlled by current. So these are the different symbolic representation, and we are not going to detail about these dependent sources. We are not going. This is not in our syllabus, so we are not going for to see what are these kind of dependent sources. So this is we are going to study in the coming. When you are entering into the second year, you are going to study this class, this particular concepts. Now come to, we will see what is ideal and what is a practical voltage source, and what is ideal current and what is that practical current source. Now we'll go to see what is ideal ideal voltage source here. So already what is the ideal voltage source we have defined. So that is the voltage source which has to provide the constant voltage irrespective of the current drawn. So that is the definition we have gone through. So we already seen that. So this is my ideal voltage source. Terminal is there, this is Vs, and from this terminal my load has been connected. In between the AB terminal, load is there, and my IL, and this is IS, whatever the voltage VL. So irrespective of my load, the load current drawn, that's load current drawn, always my voltage source has to provide the constant current. For that we also seen the characteristics for this IL versus the VL. This is going to getting a straight line, isn't it? This is Vs. So VL is equal to Vs. So this is what we already gone through this. Now come back to what is the practical voltage source. Practical voltage source. So this is what I need to explain here. What is practical voltage source? So in the case of practical voltage source, the resistance of the practical voltage source is not zero. The voltage source resistance is not zero. Voltage source resistance is not zero. Resistance is not zero, but it has exists some resistance, some value is there. The resistance of this particular source has some value of R, value R. So if you consider this resistance to that voltage source, and if you redraw the practical voltage source, so this could be like this, and this is my Vs, and this is the RS is a resistance, some resistance value of your voltage source, and this is my AB terminal. Now see here, the ideal voltage source and the practical voltage source. Here I am not considering any internal resistance of this particular this specific voltage source here, but when it comes to the practical voltage source, in the practical case, we does not omit the internal resistance of the voltage source, so we need to represent that. So this is what Vs in series with the Rs can be represented here, and this is called, you can call it is as the practical voltage source. You take one note here. Note, for ideal voltage source, the the internal resistance of this voltage source is 0. So that is what you need to know the point here. Okay, come now. So I'm considering, I'm going to draw a load here. I'm going to connect a load here. So my load is there, and this is what, and you can say this is my VL, and this is my IL, and this is IS coming like this. Okay, and now after assigning all these different values, I need to write the expressions here. So this is plus and minus, so I know RS and IS, and this is what plus and minus of this particular voltage. Now apply the KVL here. We apply that KVL here. So in this loop, apply the KVL. What you are going to get here? So Vs is equal to, this is the voltage drop. What is the voltage drop here? It is can be IS and RS. I can say IS and RS plus this voltage plus this VL. Here whatever the IS is equal to IL, right? So IS is equal to IL, right? Instead of IS, I can write IL also. So I want to explain this. V is equal to Vs minus IL into R. So this is the expression we are going to get. Now if you draw the VI characteristics for this practical voltage source here. So if you draw that IL versus VL, and here, so here my this is the point somewhere Vs is there. In practical case, this is the straight line is going, isn't it? This is the what gone through that. But in this case, as my load current is varies here, as my load current is increases in this direction, as my load current is increasing in direction, what about my VL? That is what is my about VL is going to slowly decreases, and this could be the my practical characteristics for your voltage source. This is the practical case, practical, and this is for ideal case. So this is what you need to understand of ideal versus practical voltage source. Now comes to here, I need to explain the one more concept, that is practical current source. Let me take the practical current also. So before that, you know that ideal current source. Ideal current source is the current source which is provide the constant current to the load irrespective of the voltage variations. So that is the definition in the previous class we have seen, and it's the ideal voltage source, the VI characteristics, also we have gone through that. So this is what we have seen. So this is what we have seen. So IL is equal to IS. Straight line is coming irrespective of my voltage variation. Irrespective of my voltage variation, it is giving me the straight line. So that is what constant current is, it's providing us. So that is what we have seen, and that is very simple, very we have gone through that. Okay, fine. But in the practical current source, if you see the practical current source, so for this practical current source, it has some resistance. So that is what is the resistance is represented here, and this is what is going to be called the practical current source here, IS, and this is the internal resistance. This is called internal resistance. So you can say RS is the internal resistance. RS in between these two terminals. You can write. We need to remember one note here again. In ideal case the R internal RS, that is the internal resistance of the current source, is infinite. So that's why we are not taking this RS in the ideal current source. But when you are going to consider here, so this practical current source has some resistance, and which has been represented in this manner here. And now I'm connecting one now I'm connecting a load here. So this is my load. This is load, and I can say this is IL and this is VL, and this is what my current is coming like this. This is IS. This is the total practical current source. So from this current source, IS is the current direction is coming like this. So this is what, and you can write here IS. This is fine. And what is the current here? RS can be written as IR. So that is also equal to, you can write VL by RS. Why I'm writing VL by RS? Whatever the voltage is which is coming appearing easy, this is also appearing across your resistor RS. So that's why I'm writing IR current. IR current can be written as VL by RS. So this total voltage is appearing across your RS. So IR can be written as VL by RS. Now apply some KVL here, KCL, you apply that. So my current IS equal to this IR plus IL. Can I write like this? So this is the node I am considering, and for this node I am applying that KCL, and IS is equal to IR plus IL, writing. And I can write here IL is equal to, I need IS minus this thing I need to write IS minus IR. So my IS is equal to, what is IR here? This value I can write VL by RS. This is the equation we are getting to study the characteristics. Now if you draw the characteristics here, this is what VL versus this IL, and some point here it is my IS is there. This is what the practical ideal case is going like this. But when it comes to the practical case, so this is my equation. In this equation, if my load current is varying in this direction, this is my load current is varies. As this load current is varies, what is my IL current? So that is what IL current is going to slowly decreases, comes like this. So this is what the practical case characteristics, and this is the ideal characteristics for your current and voltage source. And I hope that I think you understood the concept of what is ideal current source and practical current source, and ideal voltage source and practical voltage source. So we'll stop this today, and we'll continue the then on some other topics in the coming class.